When they ask us, is this function continuous? We are thinking about, are there any holes or are there any vertical asymptotes? Remember, to find holes, we're going to factor and cancel, and we're going to set what x canceled out as equal to 0, and that's how we're going to find our hole. For vertical asymptotes, we'll take the simplified rational function, which I call the surviving function, and set the denominator equal to 0. So usually I look for holes first. I'm looking for these removable discontinuities. So I can make this factor into x minus 5, x minus 3 in the numerator, and in the denominator, I can say this is x minus 5, x minus 1. You can see that I'm canceling out x minus 5. I can do this because I'm multiplying in factored form. You can cancel only across multiplication. In other words, I can't cancel those x squareds in the beginning. I can't divide 5 into 15 because that plus sign and those minus signs prevent me. So my surviving function is x minus 3 over x minus 1. By the way, anytime I factor, I can always FOIL to make sure I've got the original. So I'm checking that. Yep, that works. And this works as well. So FOIL, I just did it mentally to make sure you factored correctly. All right. So if I canceled x minus 5, I set that equal to 0 and I get x equals 5. We know that holes are of the form x, y. So look what I have so far. X is 5. Let's find the function value at 5. Now, to find the function value, I'm going to go to that simplified rational function, or what I call simply the surviving function here. This is where we look to find the y of the whole. So that's 5 minus 3 over 5 minus 1, which is 2 over 4, or 1/2. So that tells us we've got a hole at 5 1/2. That's our removable point of discontinuity. The second thing I'm going to look for is vertical asymptotes. I set the denominator of the surviving or simplified rational function equal to 0, and I get x equals 1. And here is my infinite non-removable point of discontinuity or spot of discontinuity. This one is a hole, it's removable, and this one's a vertical asymptote, and we call that an infinite discontinuity. We say this is non-removable. Remember, the hole was the only one that was considered removable. Is this function continuous at x equals 3? That's the question. Well, I don't even have to graph it. I can just put in 3, even though I know x can never equal 3 for this top function, where x equals 3 is the bottom function. But I could see where the trend in y is going towards here. This would be 5 times 3 plus 7. 15 plus 7 is y is headed towards 22. For this bottom function here, I can say, I'm legitimately allowed to say that x is equal to 3. If I put in a 3 for x, I'd have 7 times 3 plus 1 is 21 plus 1 is 22. Look, the y values are headed to the same place. I can be quite confident that the function is continuous at x equals 3 because I do have that actual point, x equals 3, there. Now, if I wanted to graph that, I don't even have to graph it. I know the answer, but if I wanted to graph that, I'm interested in x equals 3, and we'll say here is our point, 22. The red function is only allowed for x is less than 3. 5x plus 7 is going to be something that looks like this, and we have an open circle there, but 7x plus 1 is going to have a steeper slope, and it's also going to go through this point, and we're allowed that blue spot there. So our graph would look something like this, and you can see that we've met all 3 conditions. The limit as x squeezes in on 3 from the left is 22. The limit as x squeezes in on 3 from the right is 22 because the y values are heading to 22. What about the function value at 3? It's also 22. So our 3 conditions for continuity have been met. So you say, yes, the function is continuous at x equals 3. If I'm asked, is this function continuous at x equals 3? Well, I know that x is not equal to 3 with this top function, but I still want to see where y is heading towards as I put a 3 in there. This would be 4 times 3 squared minus 2 times 3. 3 squared is 9 times 4 is 36 minus 6 is 30. So this function is heading towards a y value of 30. How about this middle function? If I put in a 3 for x, I get 10 times 3 minus 1. 30 minus 1 is 29. I can already tell the function is not continuous. And for all values of x greater than 3, I'm going to get 30 here. So 30 matches up there, but 29 is present there. So this will not be a continuous function. Let's see what the graph looks like. So if I graph the top graph, I know that's a parabola. Look, if I put a 0 in for x, I go through this point right here, which is 0, 0. I know it's a parabola that opens up because our first term is positive. And we found out that when x is 3, y is 30. So here's our point, 3, 30, which we're not allowed. That's why I drew an open circle there. And for the red function, we're also not allowed this point, 330, because for the red function, x is only greater than 3. So when y is equal to 30, we get a horizontal line at 30. Here's the kicker. When x is equal to 3, y is 29. So we get this point right here. You can see that the limit from the left, at the limit as x approaches 3 from the left is 30. The y values are heading towards 30. The limit as x approaches 3 from the right is 30. But the function value at 3 is 29. Wah, wah, wah. We passed the first two rules for continuity, but we failed in the third. And so, because the left-hand limit is equal to the right-hand limit, we say that we have a whole removable discontinuity, or you want to call it a whole point, fine. So if we're looking at this graph, we're asked what kind of discontinuities do we have? I like to go left to right. So at x equals -4, we've got, looks like we're missing a point there. So we have whole discontinuity. I'm just going to write D for discontinuity. That's a removable discontinuity. Look at x equals -3, we've got infinite discontinuity. I'll write D for discontinuity. Remember, that is non-removable. Oh, look at -2. At x equals -2, we're jumping y values. The limit as x approaches -2 from the left is -1. The limit as x approaches -2 from the right is 5. So this is jump discontinuity. Over here at x equals 3, look, the y values are going off the chart towards the vertical asymptote and off the chart this way to the vertical asymptote. So we say infinite, infinite discontinuity. Remember, that's non-removable as well. It doesn't matter if these are both going to negative infinity or if one is going to positive infinity and one is going towards negative infinity. The limit does not exist because this is not a real number there. And finally, at x equals 4, well, let's see. The limit from the left-hand side as x approaches 4 from the left is -3. The limit from the right-hand side is also -3. So this is simply a whole discontinuity. Now we had a does not exist, the actual function value. It wouldn't matter if we put this point there and made it some sort of piecewise function. The limit still is -3 from the left-hand and right-hand side. But whether that point is there or not, we have a whole discontinuity.